Hi, everybody. Hope you have a nice weekend. We are getting close to the end. Phase transitions. We are approaching one more lecture, and the next week we start chemical equilibrium. And I'm going to kind of hint at chemical equilibrium today and in the next class as well. We'll try to use our discussion of phase transitions to get our sense of this concept of free energy today, right? And see what we can do with it. And of course, you guys are intimately familiar with Gibbs free energy, and you didn't even know it. Even if you haven't, you might remember it from Gen Chem. But the entire concept of chemistry in the macroscopic scale, the way we determine the viability of chemical processes at given conditions, is Gibbs free. And I want to try to get to the point using phase transitions as our motivation to appreciate the subtleties of Gibbs free energy, and explore what it teaches us. And so this is Gibbs free energy. It's just a difference of enthalpy and entropy defined only at constant pressure. That's the important thing here, constant pressure. Again, think of flask in exchange of an atmosphere or some vessel who's allowed to expand, a balloon at some fixed pressure. This is where Gibbs free energy works. There are other types of free energy for other conditions. There is something called Helmholtz free energy, which is very useful at constant temperature, constant volume sometimes. It's very useful in engineering. We're not going to worry about it too much. Same interpretations, just a different condition. And so the idea of free energy is the important thing here. And so I want to drive home the idea of what free energy is. What can we learn from it? What does it mean for energy to be free? And the best way to think about free energy is it's what's left over after a process. It's the way I like to think about it. In some sense that there's some imbalance of energy between entropy and enthalpy. And Gibbs free energy tells us about that balance. And I want to use the phase transitions to explore the balance of enthalpy and entropy. What are the differences between the two? And why is the balance important? So what I want to first look at is just to motivate our conversation is to go back to carbon dioxide. I drew a figure like this many weeks ago for compressing carbon dioxide, which where we discovered phase transitions the first time. So this is the plot of that. So CO2, these are what are called isotherms, right? These are compression curves for carbon dioxide at different temperatures. Right? So this is dT equals 0. Right, and just like we saw what we discussed before, there is clearly a temperature in which liquids turn on. Right? And the critical point is where those conditions where it turns on. Right, and I could kind of, in some sense, demarcate, right, the isotherms or the behavior of the material along this line that I've drawn in green here, right, where everything above that point acts like a gas, right? Everything up here is ideal gas-like, right? Where the pressure of the system is just RT over the volume. And you see the units of volume are a little strange here. These are engineering units, cubic meters per kilogram, but again, you can convert this into lower volumes, no problem. So everything past this point, I should probably use a better color than green. Everything past this point is ideal gas-like. It compresses like an ideal gas, and then everything below it is a little funky, right? Because condensation kicks in. Right, so inside of this region that's drawn here, right, condensed condensation where the liquid is occurring. And so let's think about it from this perspective of condensation from the point of view of Gibbs free energy. Right, if we had some free energy, right, free energy means, remember last time, the positive number means that there's not enough energy in the system to complete the process spontaneously. And so in some sense for condensation, the free energy of the system changes signs from positive to negative at the point of condensation. Right? And that's this line right here, right? So if I draw that line, if I think about this line right here on the low density side, right? This is in some point the line of equilibrium. Right, where it's equally likely for the liquid to condense, right? It's where the liquid begins to condense. So liquid condenses as V goes to 0, and gas forms as you decrease the density. Right, so as I move to this direction, I form more liquid. And if I move the same way along this direction, I get more gas, right? So there's this line of equilibrium where I go from one situation where there is no energetic favorability for the liquid to form to suddenly a region where the liquid forms. And so what that means is that the free energy now has changed, right? It's now become spontaneous for the liquid to condense at these conditions. But what that means is that for these conditions, then, that this must be the point, this line says a function of temperature, where delta G, or the free energy of the system, is equal to 0. That's the equilibrium line. Right? To the right, you can't make liquid. To the left, you spontaneously. And of course, there's another line which has a slightly different interpretation. This line here, right? This line corresponds to losing gas altogether, right? It means that you've completed the condensation. So this line means on this side, if you will, if I draw it like this line means that condensation is completed. Right? And then now all you have is liquid. The left side of this is just pure liquid. Right, liquid only on the left side. So there's a couple take-home points from this discussion from Gibbs free energy, or free energy, is that the free energy changes from positive to negative for a process, at least for condensation along this line. And then what happens is, more interestingly, maybe, and we'll have to think about this a little bit, is that as you move along one of these lines at some temperature, condensation is not an instantaneous process, right? Condensation becomes more and more apparent. You condense more and more gas as you traverse along this direction. Right? It's not like all the gas just simultaneously condenses. Condensation, it's not an on-off switch in the sense that there's nothing here and only things here. No, it condenses all out immediately. But condensation is a continuous process along this curve. So we have a process that's gradual along this curve. We move along temperature, it's gradual. And then imagine I do a different direction. Right, so the first direction I'm implying is that I go from this point 1, to point 2, right? And I only just condense more. Nothing interesting happens. Just condense. Just more liquid condenses. Now, what happens if I keep specific volume constant and I turn off my gas, turn off my CO2 feed, and I instead heat? Right. So if I continue, let me erase this condensation. Right. What if I just keep it fixed and now I move? What's a good color for this? Yellow. No, that's probably a bad color. And I move along this olive line to here. Right. I move along some other line here. The point 3. What do I also see? Well, I'm coming into a situation, right? What happens is I'm continuously losing more and more gas. Right, I have losing more and more liquid. I have more and more liquid here. But as you can see, as I start to approach higher up this olive line, this green edge, which is the equilibrium line, is getting closer and closer to my point, right? To the point that I'm lying on. So let's say I take it from point 2 and I move halfway up to point 3 at the next isotherm. I'm a little bit closer to that equilibrium line, which means that the gas is more favorable. So here I have less liquid and more gas than I had at the first point. And then suddenly what happens is I cross the green line, the equilibrium line, I've gone back into gas. And so I've boiled everything off again. All right, here's an interesting point though. What if I move just a little bit further? And so of course what I see here is only gas. But what if I move a little bit further? And instead I pass through this value K. 3 prime. And I pass through that value K, what happens? Well, in some sense, what's happened is that the amount of liquid that I have in my flask is getting less and less smooth, right? To the point where, in some sense, I have no more, in some sense, the liquid has smoothly disappeared, right? I get less and 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 less, and then delta G is equal to 0. And suddenly I've passed through this critical point where I only have gas now. And so what you see here, instead of a gradual condensation, you see a smooth, continuous loss of your gas. And there's some important points at this critical point. So at point K, there's an important thing that happens here. Is at first, of course, delta G is equal to 0. But also delta H is equal to delta S, which is equal to 0. This was our definition of the critical point. At all other points along this curve as I pass along, delta G is equal to 0 along the equilibrium line. But the entropy change and the enthalpy change is not equal to 0, right? This is like boiling water at 350 or 373 or 393, right? You have some enthalpy change. And so the system releases heat here, right? So there's a distinct difference here, right? This is a heat-free change. This is, in some sense, heat-free vaporization at the critical point. And here, this is vaporization with heat. So what happens is that if you move across the equilibrium line along any other point along K, there's some heat change, meaning that there's some fundamental difference between the two layers. What this also means, right? This means that the Gibbs energy of the liquid is not equal to the Gibbs energy of the gas. Oh, sorry, that's not true. Right? Which means they have different stabilities. But here, in the top case, the H liquid is equal to the H gas. They have the same stability. They're the same material. You can't tell them apart thermodynamically. So we have two distinct differences, right? If I pass through this curve, this equilibrium line at any point other than K, I evoke a heat changes because I'm changing between two distinct materials that have different enthalpies, different stabilities, and as we'll see, they're just different. And as I go towards this point, what happens is that instead, the distinguishing difference between liquids and gases disappears at that point. At this point, at K, there is no difference between the liquid and the gas. It just ceases to, the distinguishing thing ceases to exist. So we have a phase transition that occurs at one point that looks very, very different than the phase transition that occurs at all other points. But the important thing here is that they're all delta G equals 0. It's just as likely to have a liquid or a gas, just as it is just as likely at the critical point to have coexistence or no coexistence. They're both phase transitions, but clearly they have distinguishing features that are different from each other. One involves latent heat, one doesn't. And we can smoothly move between them by just traveling along this curve. Right, so So what that means is that there's something interesting in particular about this equilibrium. Delta G equals 0 tells us a lot about the behavior of a material, right? And so if we can track delta G, this equilibrium line, we understand where delta G is, we can basically predict anything about the material. It already includes everything that we know about the material, delta H and delta S. So what I want to think about now is equilibrium, this equilibrium line, right, where the phase transitions occur spontaneously. And what can we learn about them? How can we predict them, right? How are they defined? Why does it have this shape? Right? What are the shapes of these lines as we move through the different parameters that we choose? Temperature, pressure, volume, and so on. Right? So this, we can't really tackle, as I said, we can't really tackle this curve from the perspective of Gibbs free energy because it's not constant pressure. Right? Pressure is the response variable. This is at constant temperature. So what we need to do is reformulate this idea from the perspective of constant pressure. So we want to apply Gibbs energy here to phase equilibrium. To look for the G equals 0 line in terms of the independent parameters of the system. All right, what can we change in this system? Well, we defined Gibbs free energy last time. Defined as a function whose input parameters are the number of particles, the pressure, and the temperature. Okay. And for this system, we're going to define a couple things. We're going to define N as to be the particle number of liquid particles plus the number of gas particles, because we have two different phases. It could be any phase or any other two phases. Right. We may also want to consider the number of solid particles as well. But we won't worry about that too much. You'll see why in a second. Some other phases. Okay. And I want to think about how delta G varies as I move the parameters, but delta G is equal to 0. So I want to think about the shape of the G equals 0 surface. The surface of parameters where G as a function of N, P, and T, where is G equal to 0? You can think about the point where G equals 0 is going to change as I change the temperature, right? We saw that, of course, on the other slide. So we're going to assume that delta G for our process is equal to 0, right? And vary along this surface, this constant surface. All right. And we do it the same way we always do, right? We're going to take the derivative of delta G and think about how it varies with its variables. All right, first, it's going to vary with respect to its temperature at constant pressure and constant particle number times the change in temperature. What's the change in Gibbs free energy with respect to the change in pressure at constant T, constant N, times the change in pressure. And then we have the change in delta G divided by the change in N, right? The change in how delta G changes as we move particles away from the different distributions at constant T and P, right? Imagine this term talks about, this is how the energy changes in, for instance, We have some equilibrium between liquid and gas, and we suck some of the gas out. How does the system respond to that? Okay, that's what we tell us. All right, just like before, we identified that these are the changes of our independent parameters of our system, NP and T. And they're multiplied by the derivatives of the partials, right, which are the slopes in some sense with respect to those particles, right? And we can identify these as the dependent parameters of our system, and we can give them labels, right? Just like we've always done. And these labels are no different than any other type of energy, right? When we talked about total energy U and a constant temperature process, we talked about entropy and how temperature and entropy are related through this process or through this relationship. We can do the exact same thing and nothing's changed. So what we can do is say, well, if we've got a derivative of energy with respect to T, a constant other things, when we had something that looked like this in our other instances, we know that this has something to do with the other variable associated with temperature, which is entropy. So this has to be some related somehow to entropy. Here we have a change in energy with respect to P, right? The conjugate variable of pressure is volume, so this has something to do with volume. And here this has something obviously to do with chemical potential, right? We're going to find out that this is where chemical equilibrium arrives, right? So we'll come back to this term again. I keep pushing it off, but we're very, very close now. Chemical equilibrium is where this plays, right? Because this tells you how the energy changes or delta G. The equilibrium changes as you change the number of particles on either side of the interface, right? You remove some liquid, add some liquid, remove some gas, add some gas. How does it gives energy? How does the equilibrium changes do that? That's just Le Chatelier's principle. Right? So this is, in some sense, right? So what we can immediately identify, for instance, is that this is equal to the molar volume. We should do the math. And this term is equal to minus the entropy. So there's a minus sign that comes up. Right? The math is not so important. The minus sign here. And here, this is the chemical potential for the system. All right, we're going to see again that this controls chemical equilibrium. Le Chatelier's analysis, Le Chatelier's principle is derived off of chemical potential. We're going to talk about that next week's topic too. But here's some really, really, really nice relationships. If we look delta G is we change the pressure of the system as we move pressure up and down. Delta G, the equilibrium line changes as the molar volume of the material, or the change in molar volume. These are changes. So I should say delta V and delta mu. Right? How the molar volume of the material changes. Right? Well, so again, remember molar volume is something with density, right? The inverse of density. Right? So for instance, for a liquid to a gas or a solid to a gas, sublimation, this is a very large number, right? Because the gas has a very low density, very large molar volume, and the solid has a very tight volume, very small volume, very large density. This term is very big, right? So sublimation, the equilibrium line for sublimation between solid and gas changes a lot as a function of pressure. Same for delta T, right? Things that change a lot in entropy, say solid to gas, the variability of that equilibrium line with respect to delta S, or with respect to T, sorry, is going to be large because delta S is large. But between a liquid and a gas, it's a little smaller, or two different gases, very small. And then we'll have to come back and think about this. This is Le Chatelier's principle. So we'll come back. Right? And remember that the idea is that we're considering all of this equal to zero. Right? We're interested about the region where this total change is equal to zero. We're at equilibrium. All right, so what can we learn from this? Well, the first thing we can do is say a very simple conclusion. This is that the change in delta G, the change in G, We have these two relationships now. And so we have these nice relationships. What we can do is just integrate these. Right? So we could say that delta G at some temperature minus delta G at some standard temperature is equal to minus the integral of the change in entropy with respect to temperature from our standard conditions to our final conditions. And then it gives energy as a function of pressure with respect to some standard condition. The integral, sorry, wrong integral, of the molar volume, change in the molar volume with respect to pressure. Right? So if we assume delta S is temperature independent, which it's not, but let's just make that assumption. We could calculate the value of delta G at any temperature by calculating the value of delta G at some point and taking the difference of the energy and multiplying it by delta T. Right? And if T naught is your equilibrium point, right? And we write the same thing here. We can write that the delta G at any pressure is equal to delta G at a standard pressure plus the change in the molar volume times the change in the pressure. Right. So here we're assuming that delta V is pressure independent. Which we say means it's incompressible. And you're looking at that in problem 1 on the homework right now. Right. You're also looking a little bit at this other one, slightly different perspective in problem 2. So, but the important thing here is that if I can move T and P, right, I can track how delta G changes. Right. So what I can do now is I can, right. So now I in some sense have a formula or some way to measure where the equilibrium line moves as I move T and P in my system. As I heat it up, as I pressurize it, as I depressurize it, cool it, I can figure out where delta G is equal to 0. Because delta G varies with my two parameters with the change in molar volume, that's easy for you to measure. You just need a graduating cylinder and the change in entropy. So a little trickier, but there's ways to do it. You've already talked a little bit about that. Heat capacity will give you that information. So now what I can do is by using heat capacity, by using calorimetry, and by using graduated cylinders effectively and measurements, I can measure where the equilibrium line lies. That's what you're doing in the solid liquid phase diagram lab in rotation right now in PCAP. There, we're just keeping pressure to be equal to 1 bar. You're not varying along this. You're varying along this. So what I want to do is I want to plot the delta G equals 0 line on a graph of T and P. Right? Those are my two independent parameters, and I want to calculate where the equilibrium line lies. Okay, so I've got a T and P curve here. And I want to think now about how delta G equals 0 varies with T and P. All right, so what factors do we know? Well, first we know that the derivative of delta G with respect to P at constant temperature is equal to the molar volume. I'm sorry, the change in delta G with respect to temperature at constant pressure is equal to minus the change in entropy, or minus entropy. And I know that delta G is equal to 0 at this equilibrium line. So that means that minus SDT plus VDP, which is equal to delta G, is equal to 0. Right? So we have the relationship that SDT is equal to minus VDP. And by putting all of this together, right, now what I can do is I want to calculate now. Oh, is this your scarf here? Yeah, there you go. You're welcome. Right now I want to calculate lines of values T and P where delta G is equal to 0, which means I need to think about the slope of the line with respect to T and P, right? I need to think about dy dx, which is going to be dp dt. I want to calculate dp dt such that delta G is equal to 0, right? And I can do that. I have dt and dp here. Right? I can just divide them two. And what I get is an equation that's very, very nice. It says that these phase boundaries, the slope of them, is just equal to delta S over T delta V. This is called the Clapeyron equation. And just like we said before, right, delta G varies with these two parameters. So any line where delta G is constrained, here we're constrained to be 0, has to be a function of those parameters. And that's just a function of T, delta V, and S. But we know how the entropy changes through a material as you go through a phase transition or delta V. Obviously, that may change a lot for certain things. You know the temperature, you can calculate the slope of that line. So what I can do is go measure, set T and P and let the system to equilibrate. Find a place where you have equal amounts of liquid and gas. And I can measure exactly delta S and delta V for that system and the temperature and know exactly how the slope of that line occurs at that point in T and P. So let's work this out intuitively. Right? We're not going to do any numbers, right? All we need to do is think about how does V change, or the density of the material change as we go across the boundary, and how does delta S change as we go across the boundary. So all we have to do is just make a list of the different phases, and then just calculate in our head, is it going to be positive, is it going to be negative? And then we know the signs. And we even can measure the magnitude, maybe, of the slopes, how steep they are, or how shallow they are. Because all we need to know are the signs. So let's work that out. What I'm going to do is this. Right, we're we're going to take two different phases. And we're going to just use intuition, calculate the sign of delta S and the sign of delta V bar. Which is equal to the change in 1 over the density. Okay, remember that. All right, so let's just think about it a little bit. All right, so let's just start. Let's do gas to liquid. All right, let's do some other ones. We have liquid to solid. And solid to gas. And of course, we can flip these. We should flip them and think about them and just make sure everything makes sense. And then finally, what we need to calculate is just the sign and rough magnitude of the slope of the curve dp dt, the phase boundary, right? Which is equal to delta S over T delta V. Okay. So let's do gas and liquid, right? So remember that we're going from gas to liquid, okay? So which is more of a disordered material, gas or liquid? Gas. So is delta S negative or positive? I heard it. What's up? Negative. Right? It's negative, right? We lose entropy because we're going from a disordered material to a more ordered material. Now, what about molar volume? Gas has a higher or lower molar volume than liquid. Let me ask you this question. You guys, here's a good way to tell this. What's the molar volume of H2O liquid? How many milliliters of water do you need to have 1 mole of water? Roughly. Anyone know? What's the density of water? 1. So it's 1 what? 1 gram per milliliter, right? What's the molar mass of water? How many milliliters do you need? There you go. It's 0.018 liters per mole of water. Now for gas at the same conditions, does anyone know how much volume you need for 1 mole of an ideal gas? Does anyone remember that number from like a million years ago? Yeah. Okay. So it's not really any different for any other liquid and gas, right? They're all the same. So easy to remember this, right? So gas to liquid is a positive number. Sorry, no, it's not. Negative number. All right, gas to liquid, not liquid to gas. Right, so we can just do the sign, right? We have 2 negative numbers. T is always positive. This is greater than 0. We know that as you increase temperature, the pressure required, therefore, to liquefy increases. Right? So this means that as T increases, vapor pressure increases. Okay. That's all that means. Let me just mark this off so we have the space. Right, so let's just do the same analysis, right? Liquid to solid, right? Again, we have delta S is less than 0, right? And we're going from a less dense material to a more dense material. The V is less than 0. We're greater than 0. All right, but let's look at solid to gas, right? Solid to gas here, entropy is increasing. And the molar volume is obviously increasing. Right? And this is also greater than 0. Right, so we've in some sense not really done anything interesting. They're all positive. There's an exception, though. Aqua to ice. Aqua, I mean aqueous water. Ice. Using that distinguishment liquid. right? This is clearly delta less than 0. But what do you know about ice relative to water? Dense or more dense? Less or more? Less. So this is flipped. Right? So that means that the sign is opposite for the solidus line, the freezing line. Water has a freezing line of opposite direction. Right? Instead of bending forward as you increase the pressure, it bends backwards. Now we can also think a little bit about the magnitude of this. Right? We've identified the signs. We really quite haven't identified the magnitude, whether they're like super steep or they're really shallow. And of course, it's going to depend on the conditions. But we can roughly talk a little bit about it, right? Because the steepness of the curve is going to depend on the magnitudes of the values. And so if delta S is really, really big, or delta V is really, really small, the slope's going to be really large. Meanwhile, if they're about the same value or they're both very close to 0, then the slope's going to be roughly 0. So we can look a little bit, right? So gas to liquid, for instance, delta S is less than 0, but delta V is much, much less than 0, right? It's very, very negative, right? Because you're creating a gas from a condensed material. Right, but the entropy change is also pretty significant. In fact, if you go, one of the things that you'll calculate in problem mark 3, if you haven't done it already, is that S change, the entropy differences between the liquid and gas for water, and it's actually significant. The change in entropy is almost 2x what it is with gas. So the delta S also changes a lot, right? And so this line is only moderately greater than 0 in slope. Delta S is, you gain a lot, lose a lot of entropy. You also lose a lot of volume change. There's a big PV change, and so the sign is moderate, right? It's not super sharp, right? It's kind of shallow, right? But what about liquid and solid? Again, the same thing here. Delta S is not really that big of a change. It can be significant, but not really in magnitude compared to gas and liquid, about the same. And the volume change really isn't that much as well. So this is also shallow. Right? This is small. And this is, we'll call this moderate. And this is large. This is large, right? Then you can see, well, solid to gas, right? Solid to gas is very, very distinctly different, right? We have a large entropy change and a large volume change. Or sorry, large volume change relative, much larger volume change relative to the, it's about the moderate here, but a large volume change. I should say moderate change, right? So you have this ends up being very sharply negative, positive, and this ends up being sharply negative as well. So the solid to liquid line, all the gas line, excuse me, tends to be quite sharp as well. So let's put this all together. Let's look at a phase diagram. Well, let's just convince ourselves of the correct thing, right? So I'm just going to pull up a random molecule. So we'll just look at the phase diagram for CO2. Right, so this is the phase diagram for carbon dioxide. So let's look at some of these regions and just try to understand what we see here. Well, again, remember the slope that we're measuring, right, So we take a random point here and we draw a tangent line to that point. Right, and the slope is equal to dp dt. Slope is equal to that, sorry. Right, we can see between liquid and gas, right? In liquid and gas, we have a moderate change in entropy and a moderate change in molar volume, or a large in both, however you want to think about it, right? So we have a shallow slope here like we predict. You can see here that the solid to liquid line, the sublimation, right? This has large delta V and large delta S, but T is small. Right? T is low. So the slope is somewhat moderate here. Right? And then if you notice, the interesting thing, of course, is solid to liquid. Right here we have V small, delta S small, and here we have V large and delta S large. Right? And you can see we have a large slope, right? Very, very steep slope. And this has a very steep slope. Right, but you may notice, and this is the interesting thing, right? They all have somewhat of a bowing curvature, right? They're all kind of slowly approaching kind of a flat curve as you go along. Maybe we can appreciate a little bit this curve here, why it seems to be leveling out, because we know exactly where this approaches, right? This limit ends right here at this critical point. I mean, critical point, the difference between the liquid and the gas disappears. So everything here, liquid and gas, are exactly the same, right? So the system, the slope is just basically going to zero as we get to this point, because delta S is going to zero and delta V is going to zero because they're becoming the same material. So this slope, right? So as we go up the slope here, liquid and gas are converging. They're becoming the same. Right? But what happens if you think about the other line that we see here? Here it's very, very steep. Right? The reason why it's very steep here, of course, is that T is very small. It's very, very steep curve, and then starts to bow. And you might say, well, what happens if doesn't the same thing happen? Right? Is there a critical point up here? Right. Why is it that, first of all, why is it that this curve in particular bows for solid to liquid very dramatically, right? It's very, very steep early and it just bows off. It's an interesting question to ask. But why does dp dt for this line go to zero? I want to think a little bit about that. Well, the fact of the matter is that no matter what the temperature or the pressure is, delta S is not equal to zero between the solid and the liquid. So it never reaches this point. Right? I'm trying to explain that to you today. Right? What about delta V? Well, the molar volume of the solid changes very little. With P and T, right? Right. You can imagine that graphite is graphite basically no matter what temperature you pick, right? It's just a boring old solid. It's just a rock, right? There's not much rocks do with pressure or temperature. They're just rocks. But the molar volume of the liquid changes a lot with temperature, right? Because you vaporize it, right? You have gas. Changes a lot with temperature and is mildly compressible. Right? What does that mean? That means that the derivative of the volume of the liquid with respect to pressure is less than zero. Right? The liquid is getting, as you compress the liquid, the molar volume is getting smaller. Right? It's very hard to compress a liquid, but we're at really, really high pressure. Atmospheric pressure is like, so atmospheric pressure, this is 31 C. Right? We're kind of like right here. Right? This is where we are in atmosphere. These are very high pressures. Up there, carbon dioxide, the liquid will compress. And so the molar volume changes. It gets smaller. So what that means is that the derivative of the pressure with respect to temperature, which is equal to delta S over T delta V, right? This number gets smaller. This number gets larger, faster. And this stays constant. Well, roughly. And so that means that it starts to approach zero as T increases. Right? Delta S doesn't change too much. Delta V gets closer and closer together, but T also gets larger but faster. So eventually the denominator dominates and it just goes to zero. But this is an interesting point. So here's the interesting distinction between these two curves. There's a point, right, where the phase difference, where the phases vanish. And the fact of the matter is this can never happen for solids and liquids. There is no solid critical point. Why is that? Right? Why is it that this just doesn't happen universally for any material? It does, but only between the liquid and the gas. And the reason why is because solid is in some sense a different, fundamentally different material than the liquid and the gas. There is in some sense a change in motion that you have to do to go from a liquid or a gas to a solid that never goes away regardless of the temperature, pressure, or the conditions. The fundamental change that has to occur that therefore you always have delta S is not equal to zero. And so it doesn't matter the conditions. That disappears for the liquid and the solid, or liquid and the gas. And that's the critical point. That never happens with the solid because there's something left over that you always have to change. And I want to explain that to you in the last couple minutes here. So why is that? There's no critical point. Why isn't it just heat it all up and it's all the same goop? Eventually that may be the case. You get so high in temperature, everything becomes a plasma. Just remove all the electrons, everything just positive charges and negative charges, you have a plasma. That can happen. That's a different thing altogether. But we're talking about things that happen kind of in like chemical space. We have a critical point that happens for carbon dioxide very, very close to normal conditions. Right? It's 30 degrees. It's not very exotic. Why is there nothing like this for solids? The way you can explain this is very simple. You don't have, it doesn't require any math. To understand why this happens quantitatively is extremely complicated. And one of the reasons there are a number of Nobel Prizes associated with this work. Very, very complicated, but the understanding is very simple. Kind of the qualitative idea. I just want to have my picture, my right pictures up. What I want you to think about a little bit is how does the morphology, the topology, the material change as a function of how you cut it into pieces? So let me explain what I mean by that. Imagine you have 3 different flasks. They can be in 3 different conditions, that's fine. Right? we had three different conditions. These are more like decanters than they are flasks. That's okay. Three different flasks that have the same material in three different phases. Maybe it's sodium chloride. Or whatever you want. All right, so one's got gas. One's pure gas. All right, one's a liquid. And one's a solid. All right, maybe crystalline, may not be. This is my solid. Same material. All right, what I'm going to do is I'm going to cut out little pieces. All right, I'm going to take little samples like I'm doing forensics. Take a little sample. All right, so maybe I'll cut this part out right here. Cut out this little section right here out of each section. Well, of course, I have to take statistics, so I have to do this many times. So I'll take another section, just like this. I'll cut this part out. Let's do a different place. All right, I'll take a little square out here. All right, so two different cuts. All right, this is at some temperature, pressure, everything's consistent. Each one has a different temperature and pressure. Two cuts, each the same size, the same volume across all three flasks. All right, and then what I do is I go into each of my bulk material and I measure some properties of it. All right, so for this one I measure, call it T solid, and the density. All right, we'll just measure density, okay? And then we measure T liquid, rho liquid, and T gas, rho gas. Okay, we'll just stick some thermometers in there. And then what I do is I look at each of those cuts. Okay. So I've got these two cuts here. One's a cube. And I've got some gas particles in here, of course. Okay. And I measured the same thing. Right. So for this purple cut, I measure the T gas for the first cut and the density of the gas for the first cut. And then I measure temperature 2 for the measurement for the temperature at that point and the density of the gas at that point. Okay. And I do this for all the materials. Right? I do this for the solid and then I do this for the liquid. Okay. And then I do it for the solid. All right, we'll come back to the solid. Let me ask you this question. Okay, I make any cuts I want, right? Or imagine this isn't at equilibrium, right? Everything's equilibrated, that's some constant temperature, constant pressure, everything's normal. Well, to sit and relax. Equilibrated to the roof. And I make these cuts. And I make sure that the cuts are not perturbed. Okay. So I'm just taking little samples. Will the temperature and the density vary? Will the temperature or the density of those two cuts be different than the bulk? Yes or no? The answer is the same for both gas and liquid. What happens when you take a bottle of water and share it with your friend and they experience a different water sample than you do? Yes or no? These are really easy questions. No. Water is exactly the same. right? It's got the same pH, it's got the same density, it's got the same temperature, it's got everything. Exactly the same, right? So you can be guaranteed that for the liquid, and this is also true for the gas, it's not hard to think about this in your head, right? If you have a balloon full of helium and you and your friend share it, and you guys are huffing, I don't know, whatever, who gets huffing, galaxy gas, galaxy gas, and you each take half the bottle, you both experience galaxy gas at the same density, the same time, right? Or if you share it amongst 30 friends, you all experience the same sample. Okay, so for both of these materials, right, regardless of cut, the density of the gas or the liquid and the temperature of the gas or the liquid are same. Right? We call this an isotropic material. Right? It's the same at all points. Right? Same density, same temperature. Now, what about the solids? Well, turns out we have two choices for solids. Right? It depends on the material, but there's two kind of general ideas for solids. There's what are called amorphous solids, like sand, right, and crystalline. Right? What if it were amorphous? Right? This is like sand, or like a powder. And I go look, and what do I see? Well, I see some particles that are very small, nice small particulates. So small that my computer doesn't like it. And maybe there's some bigger particulates. Right? Maybe there's some like some stringy looking stuff. Right? And then I take another section. And what do I find? Well, I find that they're all clumpy over here. Maybe there's a lot more clumps. Right. So what can I say about these? Well, what I can say, well, for instance, it's probably the case that the temperatures are the same. It's probably fair. But the densities are certainly not. Sorry, this should be a solid, not gas. Definitely not the same. Not area. It's like finding a needle in a haystack, right? It's just totally random. Right? You can even show, especially this is also the case, this is kind of subtle, is that the heat capacity of the first cut is not the same as the heat capacity of the second cut. Heat capacity depends on the density of the material, how much heat you can put. Right? Highly dispersed material, not very good heat capacity. Really tightly packed material, really dense material, very, very good heat capacity. Right? Give me the same material. Doesn't have to be a different chemical. The heat capacity is a difference. And then crystalline materials is a completely different subject. But in a crystalline material, let me go to the next page for this. Yeah, let's go to the next page for this. And for crystalline material, it's even more dramatic. Let me show you what I mean. All right, let me show you what a crystal looks like. Right, crystals are made up of individual And what's the word I'm looking for? I mean, you can't cut them apart. Fundamental units, call them fundamental units. Called unit cells. Right. So here's what a unit cell diamond looks like. So this is a diamond unit cell. Right. And so diamond forms these structures called unit cells, and a crystal in diamond is just a tessellation, just a repeat of these sets. Right? See, there's like a diamond is not just carbon itself, but really it's this unit, the indistinguishable unit of a crystal is the unit cell itself. And so if you think about this as being a cube with some things inside of it. So if I draw it and I mark it as like a cube, as you can see, it has a cubic structure. Right. Then an actual crystal would look something like this microscopically. There'd be one of these, and then right next to it, there'd be another one. There'd be another one. I didn't really do these aligned. Right? Just a tessellation of them, right? This would be an actual diamond. Okay, so this is what the structure of diamond looks like. Now, imagine I have this beautiful diamond in a room, 100 carats, massive diamond, worth millions of dollars for some reason. Just carbon. Turns out graphene black is more expensive per gram than diamond. But that's can't make pretty things out of graphene because it's not air stable. Now imagine, right, I have a flask that looks like this, right? It's just this giant diamond, and now I start to make cuts. Right? I make some cuts. Maybe I'm really good. I'm a really good diamond cutter, and I make a cut along the unit cells, right, along the edges. Right? And I cut that, and I cut another piece like that, and I cut along the unit cells. And I'll do it on this one. So on the other cut will be this one. Cut this one out. Right? They may have different amounts of unit cells, right? But they're still just cut down the lines. And so I have, so like cut one has, or cut two has N2 unit cells. And this has N1 unit cells. And a unit cell takes up a certain amount of space. So the density of these two cuts is the same. Right. So N1, or sorry, so row 1 is going to be N1 over V1. And row 2 is N2 over V2. Right. And so row 1 is equal to row 2. There's the same number of cuts, or same number of unit cells. Or the unit cells the volume expands the same amount as the unit cells do, so they're equal. And of course, T1 is equal to T2. Okay, so a diamond I can cut and it's exactly the same. Right? As long as I cut along the edges, the unit cell edges, and I separate the crystal into individual sets of unit cells. The densities are the same at large A. But what happens if I cut down the middle? What if I'm like, I don't know if you guys watch jewelry TikTok, but Moses is a jeweler in Manhattan. He's a terrible jeweler. I hate his work. He does terrible jewelry and then overpriced sells it. So what he does, Moses the jeweler just cuts down the middle. He just says, fuck it. I'm just going to cut like this. Cut down the middle of this diamond. Through the unit cell, not along the natural lines. Right? And he cuts out this region right here. And then he says, you know what, I'm just going to take another part, like right here. Right. So Moses the jeweler takes these out just for the clout. He's got to ice out that chrome hearts jewelry to make an extra 10 grand, putting shitty diamonds on it. And then, so he takes these two chunks, right? And now you have chunks that are cut, are not along the edges. And so now the number of carbon atoms you might have in one cut per unit volume is different than you have in cut two. Right? So then, therefore, nu one is not equal to nu two, even though T1 and T2 might be the same. Okay. So what that means is that when you cut a solid material, general, except for a very, very specific situation, when it comes to crystals, you're not guaranteed to have the same material, right? It has a different density, different temperature, perhaps a different heat capacity. And of course, so with diamonds, of course, they have different lusters, different color, different inclusions, different structure. Diamonds, this is completely characterized, right? Because the important thing about a diamond, what makes a good diamond, is that it has the features of a pure, clear, untarnished diamond. It has the clarity and the strength and the twinkle or whatever junk terms they use to describe diamonds, I don't remember. But they have these important diamonds, and they're all based on the idea of a perfect diamond. And a perfect diamond is one that's cut along the edges. A diamond that is perfect. And that means that in some sense, it's not this lumpy, roughly cut. It means you're cut along the edges and that you have perfect symmetry. You've maintained the cubic symmetry of the diamond. And the only way to maintain the cubic symmetry of a diamond is to cut along the cubic lines. Right, so what the conclusion here is that in liquids and gases, or what we call translationally invariant. That means that they're the same no matter how you cut or how they move around. Changes in X lead to the same place as changes in Y as changes in Z. Moving along X, Y, Z does not changes nothing. You're just in a different part of your, right? But not solids. X, Y, Z direction matters. So what's the conclusion? Well, this is why liquids and gases continuously vary and then suddenly stop. And they become the same thing, because you reach a condition where the entropy change and the enthalpy change between the two materials is zero, meaning there's no change you have to make to go from liquid to gas. Right? Every cut of that liquid is the same as every cut of the gas on the other side. So they're the same material. They have the same temperature, they have the same density, they have the same molar volume. Right? These are the variables of Gibbs. Right? Gibbs varies with entropy and volume. If the volume is the same and the entropy is the same, then they're the same material. So liquids and gases are translationally invariant. They all their properties are exactly the same. The only difference between them is in the region where delta S is different, right, along the phase boundary line, where there is a fundamental difference between the liquid and the gas, as you guys understand. But in some sense, they're the same material, just different states. Whereas a solid, no matter what temperature you're at, whatever pressure you're at, there is a fundamental change you have to make to the bulk structure of the material. You're going from a translationally invariant material to one that varies on translation. Depends on how you make the cut. That costs energy. There's a fundamental change in the entropy of the state of the material. You go from one class of material to another. And so it doesn't matter what temperature, what volume, what pressure, whatever you're at, you're always going to have to exchange some energy, because you have to change the fundamental structure of the material. So solids never disappear. Solids are always there. And because of that, we'll see this next class, is that there are many, many, many solid states, different phases of solid materials. There's only one liquid, there's only one gas. But solids, there can be many, and there can be phase transitions across multiple solid state phases. In fact, what I'm going to show you is that water doesn't have one phase. It has 18 of them. There's 18 different types of ice. So we'll look at that next class. Have a good one, guys. Yeah. Okay. Oh, did that time work for you tomorrow? Did you get my email?
Oh, I didn't get it yet. I didn't see it yet.
Oh, I asked, I have a standing meeting with this person behind you at noon tomorrow. Are you guys gonna be there for that?
Oh,
Well,
no.
it's usually Wednesday. Oh, no, sorry.
Wednesday.
Wednesday.
I don't think I'll need this.
Oh, okay. Well, anyway, I'm usually free Wednesday in the morning. When do you get off in the morning?
After this class, I have work.
Oh, I have, oh, you have work?
Well, I have work at 4, so I can drop off. So I just need to spend it. Okay. But this one, I was just, did I do something wrong finding the? Cause I you said that is not super.
Yeah, the liquid enthalpy this is the vaporization, this is the difference in enthalpies between liquid and gas. But what you're calculating here is how much does the vaporization enthalpy change? You're comparing two different enthalpies here. This is the heat capacity of just the liquid, and this is the vaporization enthalpy. What you need to do is think about how the formation enthalpy of liquid water changes with its heat capacity. So what this should be is delta H formation of the liquid, and this should be delta H formation of the liquid at 373.
Okay, so. Oh, and I find that by using this would be at 373 using, okay, and I got confused again. Wait.
No, that's okay.
I got slightly confused.
So I'm just trying to find a marker.
I thought
Here,
it-
I'll just pour it up here.
Sorry.
Do you agree with this, right? Delta H of VAP is equal to the
Yeah.
difference of the formation enthalpies.
But yeah, I know.
All right, so then delta H VAP of T of the gas plus CP of the gas
Mhm,
delta T
mhm,
minus delta HF naught of the liquid
mhm,
plus CP of the liquid delta T.
mhm.
So I'm boosting each of the formation enthalpies separately by their heat capacities,
Yeah.
right? Then there's work out the math here. So do you have delta HF standard conditions of the gas minus delta HF? I'm just rearranging terms here.
Yeah.
Liquid plus,
Yeah.
and now I have the CP of the gas minus the CP of the liquid delta T.
Mhm.
And this is equal to, so that means that delta H VAP at some temperature is going to be delta H VAP at standard conditions, which is just that enthalpy change difference, plus the change in the heat capacity dt. So what your problem was that you're conflating the formation enthalpies here with the vaporization enthalpies
Mhm.
and just boosting them using just the heat capacity for one of the materials.
Oh, it's.
But you have to boost the products and the reactants and take the difference of the two. So if you want to think about differences of enthalpies, which is your vaporization enthalpy,
Mhm.
you need to take differences of formation enthalpies, which are each proportional to their own heat capacities. And that means that you have a difference of heat capacities. And so what you really should be looking at is how the heat capacity changes from the gas to the liquid. Delta CP.
Between standard to 373.
Yeah,
Okay,
exactly.
so.
So all you need to do, you have this number.
Yeah.
So this is your value at 373.
Okay.
Delta CP is just the difference of the heat capacities. That's a subtraction.
Yeah.
And then this is your temperature at 298, and then you just need to set up delta T for 373 to properly.
Okay.
Make sure the signs are right. Because your final temperature is lower than your initial.
Okay.
Right.
Gotcha. Because I have to find it at 298. Got it.
Yeah.
Thank you.
Welcome. What's your
I
question?
think I'm still confused. I'm thinking of-
Of course.
I use this formula to find out
Uh-huh.
this when it's heat dependent. Because you have to take into account the
Yes.
right?
Yes.
So this is the answer. So when it's heat independent, it's just using the actual values that they give me without taking.
Those are the values, the 298, yeah. Those are just your literature values.
So this is just heat independent.
No, it's not heat, it is heat independent in the sense that these entropes are only defined at 298 Kelvin. So this is the correct value, the literature value at 298 Kelvin. What you're doing is there's another way to calculate delta S using your 373 values. You've done it properly here by using the Oh, I see what you're asking. Right. Okay, I'm probably asking for too much. What I want you to ultimately do is compare this value to this value. That's what I really want you to do.
Okay.
Okay, I'm sorry about
I
that.
got it. Thank you.
You're welcome. That's good enough for me.
Okay.
That temperature dependent question is for you to take everything you've done so far and just kind of summarize how important the independence versus dependence is for the entire question. Okay?
Thank you.
You're welcome.
You.
You're welcome.